All right, howdy folks. Welcome back to Professor Carbon. In this video, what we're going to do is go over an NMR structural elucidation problem. And so we're going to try to figure out what compound could possibly give the experimental evidence shown here. And as these normally go, I'll remind you that the elemental formula provides us with some very important information right off the bat. And so one of the things that I like to determine right from the get-go is the degrees of unsaturation. And, if you can never remember the formula for degrees of unsaturation, you're in good company, because I can't either. But what I try to do is always just figure out almost from scratch and just derive it. And so the idea of degrees of unsaturation is if we have a saturated hydrocarbon, in this case, I've drawn out all of the hydrogens explicitly for 1, 2, 3, 4, 5 carbons. So this is pentane. And in pentane, every carbon has 2 hydrogens. And so if we have 5 carbons in pentane, we can multiply that by 2. And then we're going to add 2 for the capping hydrogens on each end, right? So even the end carbon here has 2 hydrogens, and then it has a capping hydrogen on both sides. So a fully saturated molecule has 2 times the number of carbons, plus 1 for each end, so plus 2. And of course, anything that is less than that always has to be some kind of unsaturated functional group or a ring. And so those are the really important clues. So with C5H8, I would expect to have, let me see here, 5 times 2 is 10. Plus 2 would get me to 12. So I'd expect there to be 12 hydrogens. In this molecule, I have 8, and so I have a difference of 4. And because each degree of unsaturation, so like in a double bond, you remove 1 H from each carbon, and that double bond gives you 1 degree of unsaturation. So we're going to divide that 4 by 2. And so we end up having 2 degrees of unsaturation. And right off the bat, that gives us a clue that there's either going to be 2 double bonds or 2 rings in the system, or 1 ring and 1 double bond, or 1 triple bond, or, it can go a lot of different ways, but importantly, there's 2 to look at. Okay, the next thing I'm going to notice is that there's oxygen, but there's only 1 oxygen. Okay, and so then that could be a ketone, it could be an aldehyde, it could be an ether, and so I want to consider all of those when reviewing the information. As I've always kind of encouraged people to do, take a quick first glance at everything instead of focusing in on one little clue right off the bat. Because sometimes, you might miss something that's like a glaring hint on the other side if you're only focused on the little bit over here. So just quickly scan everything. And as I quickly scan everything, I'll notice I've got some stuff up here, and that's going to be important because it's not in the benzene rings area. So remember, benzene rings are usually above 7. And this is going to be the double bond region. And so, right off the bat, I'm going to question double bond. And then as I scan down here, I always love having singlets for 3, because that obviously has got to be a CH3. There's really no other way to give a singlet for 3. And because I'm at 1 ppm or just above 1 ppm for that, then it has to be something that is all carbon containing, so my oxygen can't be coupled to that, and so we can immediately exclude a methyl ether from our equation based on the chemical shift of that methyl peak. All right, continuing on down here, the carbon NMR is a key piece of information, and it has 1, 2, 3, 4, 5 carbons. That's important because our structural formula has 5 carbons up here. And if the number of carbons in the carbon NMR matches the number of carbons in the elemental formula, it turns out that's a key piece of information because it means we don't have any symmetry, right? So we don't have to worry about a paired disubstituted ring with 2 equivalent carbons. We don't have to worry about a symmetric ether like diethyl ether. Each carbon has its own resonance, and so we don't have to do any detective work there. The next thing we can look at here is a note about the IR. Now, we're not seeing the IR here, and so that might throw some folks off, but it's telling us that really that the only diagnostic stretch is a CC double bond, and that's an important clue because that matches at least one of our degrees of unsaturation. That matches the protons or hydrogen atoms that are in that double bond region, and most importantly as well, it matches the chemical shift of 2 of the carbon resonances, which happen to be in that sp2, what I call sp2 land, between roughly about 110 ppm and about 160 ppm, and that's where all of our double bonds show up. And so we have 2 of those, and so we immediately then can recognize we've got a CC fragment in here. And that's good. The other thing that we can notice about that CC fragment is if we go up to the hydrogen NMR here, we have 3 different signals, all of which are in that double bond region. And so that's going to be kind of handy, because there's only one way to get 3 hydrogens all around a double bond, and that's to have a terminal alkene. And that kind of makes sense with the coupling here, because these 2 look like they're not particularly split apart, and so those are going to be the kind of terminal double bond CHs on the end. And remember, we'll have a trans J value here, J, and that'll probably be about 16 hertz. We'll have a cis J of probably about 12 hertz, and then we'll have this coupling, which should be a big coupling, but it turns out it's actually a small coupling. This is the one that I think is kind of counterintuitive. It's probably only going to be about 2 hertz for that J value. And so that's the really fine one. And then the bigger ones are going to be the cis and the trans coupling to the adjacent hydrogen. And it's pretty common to have one of those hydrogens be split into a multiplet, and then the other 2 on the ends look like doublets or doublets of doublets with very fine coupling on top. So that's pretty standard. Okay, well, we only have 5 carbons, and we already have 3 of them identified as being a terminal alkene, and then being part of this methyl group. And so that really cuts down where everything else can be. So if we go then start trying to put together the other fragments, and obviously we have 2 missing carbons, so 5 minus the 3 we've already identified gets us 2. And there's another really important piece of information on that carbon NMR, and that is that 2 of those carbons appear in the oxygenated region. And so remember that oxygenated region is roughly from about 50 to about 80. And so it's kind of a nice window, and here we definitely have 2 in that range. The third one, or the last carbon here at 19, that's most likely going to be this methyl carbon, and that's going to be down in the saturated carbon NMR region. Okay, so if we only have one oxygen, and that oxygen needs to be bound to 2 carbons, then we have to have something like this, and that would give us our ether. And we have a bigger complication here now, which is our 2nd degree of unsaturation. So if our oxygen is part of an ether, and if our carbon-carbon double bond is 1 degree of unsaturation, we've got to have a ring. So we don't have more than 1 degree of unsaturation that we can explain as a carbonyl. We don't have a triple bond. If we have a double bond and something, that something's got to by definition then be a ring. And so we'll have to figure out how to put all those pieces together. And now we have some fragments here to work with. And the last piece of information, which I have not used, is these 2 hydrogens, right, kind of right smack dab in the middle. And the first thing you'll notice is that they are going to be coupled to each other, and they're going to be coupled to nothing else. And so we can tell that they're coupled to each other because that J value, the distance between the peaks, looks like it's about the same distance. And not only that, they have this slight leaning here, which kind of indicates that they go together. And the leaning isn't totally diagnostic, but certainly in this case, they're the only things with that J value, and they're separate from everything else, and they're kind of right next to each other, and they're 2 independent H's. And those are the 2 H's we're missing, because we go up to 8, and we've got 3 from the methyl and 3 from the double bond, and so those got to be it. And so anything with that bigger coupling almost has to be on the same carbon atom. And that's pretty weird then if we have a CH2 on one side of this. All right, now there's only a couple of ways that we can stitch this together. So now we have to put, one more group over here. We have to put one more group over here, one more group over here, and one more group over here. And there's a really important piece of information here as well, and that is most CH2s, remember, they don't couple to each other. But in this case, if those H's are coupling to each other, that means that we have some level of stereochemistry in this molecule. We have to have at least one stereocenter, and we would call these hydrogens then diastereotopic, and that would explain why they're inequivalent in their, quote, talking to each other. And certainly we can't have a stereocenter on the methyl group, we can't have a stereocenter on the double bond, and we can't have a stereocenter on the CH2 carbon, and so that means that this carbon here has to be our stereochemical carbon. So all the other groups got to go on that one. And so let's just kind of redraw that to make life a little bit more clear here. So we've got H, and then some squiggle, and then we've got our groups here. And if we start attaching things, we can put that CH3, and then we can put that terminal double bond, and then we're out of atoms. So if we now go back and count this, we've got 1, 2, 3, 4, 5 carbons, and we've got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And that's everything. We still have that pesky degree of unsaturation to deal with. And so what we have to do is end up connecting those 2 carbons to each other. And this gives us a stereocenter there, and it's an epoxide. And in this case, it's the epoxide of the molecule isoprene. So isoprene oxide. And that makes sense with all of our data. And so, we have the 2 oxygenated carbons right here. So those are going to be the key carbons. We've got that methyl carbon. So that's this carbon. We've got the 2 double bond carbons here. We can always go back and double check. We've got the 3 double bond hydrogens, and so that checks. We've got our CH2 unit here that shows some diastereotopic behavior, and we've got our isolated methyl group over here. And our only other clue in the IR is to have a double bond, which we certainly have. And so that's fully consistent with all of the experimental data, and it makes sense too because it's a full octet in the final molecule. So as always, these NMR problems are kind of challenging, but if you try not to focus too much on one piece of information, instead just build up some parts, and then at the end try to put them all together, hopefully you'll be able to come up with reasonable chemical structures based on the experimental spectra data. So thank you for tuning in to Professor Carbon. Please go ahead and watch the next video. And if you're curious on how to find more examples of the NMR problems, there are playlists set up in the channel. And so you should be able to go find the one that is queued to be all NMR problems for you. And you can go ahead and gain some more experience looking at these kinds of problems.